design specification for a cellular signal amplifier for home use requires careful consideration of electrical codes, specifically NEC Article 810.20. This article addresses the grounding and installation requirements for radio and television receiving equipment, which can be relevant to cellular signal amplifiers with external antennas. The product should comply with the requirements of Article 810.20 of the National Electrical Code for several reasons. Firstly, the exterior antenna is not grounded. NEC 810.20 stipulates that any outdoor antenna for radio and television reception shall be grounded in accordance with Article 810. However, there are exceptions for antennas less than 6 meters or 19.7 feet in height above the ground or roof. If the exterior antenna for this product is designed to be mounted on the roof or exterior wall of a home and is typically less than 6 meters in height, then it does not require grounding according to the NEC. Secondly, the lead-in conductor enters the building and is connected to an amplifier. NEC 810.20b states that the lead-in conductor shall be securely attached to the building and shall not be allowed to touch any other conductive surface. The lead-in conductor for this product should be designed to be securely attached to the exterior of the building and should not come into contact with any other conductive surfaces, adhering to this requirement. Thirdly, the amplifier is then connected to an indoor antenna. NEC 810.20c dictates that an indoor antenna shall be located at least 1.8 meters or 6 feet away from any other conducting surface. The indoor antenna for this product should be designed to be mounted at least 1.8 meters away from any other conducting surface to comply with this safety requirement. In addition to complying with the NEC requirements, several additional safety measures should be implemented. 1. The use of a GFI outlet should be mandatory for the amplifier. A GFI outlet provides protection against shorting and lightning strikes, enhancing the safety of the system. 2. Instructions shall be provided with the product warning users not to attempt to ground the exterior antenna or lead-in conductor. This prevents improper grounding attempts that could compromise the system's safety and performance. The cellular signal amplifier for home use is designed to comply with the requirements of NEC Article 810.20 and to provide additional safety measures to protect users from electrical hazards. The National Electrical Code NEC Article 810 covers requirements for radio and television equipment. While a cellular signal booster might not be a traditional radio or television antenna, the principles of safety related to outdoor antennas and lead-in conductors still apply. Article 810.20 specifically deals with antenna grounding. It generally requires outdoor antennas to be grounded to protect against lightning strikes and static discharge. However, there's an exception for antennas that are less than 6 meters 19.7 feet above the ground or roof. Since the exterior antenna for a home cellular amplifier is likely to fall under this height restriction, it might not strictly require grounding according to 810.20a. The lead-in conductor, the cable connecting the outdoor antenna to the amplifier, should be installed and supported properly to prevent contact with other conductive surfaces as per 810.20b. This is to minimize the risk of unintended electrical paths. Ensure the lead-in is securely fastened to the building. NEC 810.20c covers indoor antennas and requires it to be located at least 1.8 meters 6 feet away from conducting surfaces. This is also not applicable in this setup, but good to know. A ground fault circuit interrupter, or GFI, is a type of electrical outlet that quickly shuts off power if it detects a ground fault, which is when electricity flows through an unintended path, such as through a person. This can help prevent electrical shock. While a GFI outlet won't protect against a direct lightning strike, it can offer protection against smaller electrical surges and ground faults that might occur. The amplifier itself likely has internal protection mechanisms. The power supply that converts 120 volts AC to 12 volts DC likely has internal fuse protection to prevent damage from power surges. The design should consider surge protection devices, or SPDs, to protect the amplifier from voltage spikes. This could include SPD at the point where the power enters the building and potentially on the antenna cable. Even if the antenna doesn't require grounding under NEC 810.20, proper bonding and grounding of the overall system is still important. This helps ensure that all metal parts of the system are at the same electrical potential, reducing the risk of electrical shock or damage. Include clear instructions in the product documentation about proper installation, safety precautions, and the use of a GFI outlet. Emphasize that users should not attempt to ground the antenna or lead and conductor themselves. Given the statement about FCC and IC testing, any modifications to the antenna system, such as adding a grounding lock, could potentially affect the amplifier's radiated signal characteristics and void the certifications. It's crucial to avoid any modifications that could compromise compliance with FCC and IC regulations. Compliance with UL standards for the power supply is important, but the entire amplifier system should also undergo safety testing to ensure it meets relevant electrical safety standards. This might involve testing for insulation resistance, leakage current, and other potential hazards. The amplifier should be designed to prevent the ingress of water and dust, which could lead to corrosion and electrical problems. The housing should be appropriately sealed and constructed from materials that are resistant to environmental factors. Consider using shielded cables for the antenna lead-in and other connections to minimize electromagnetic interference, EMI, and radio frequency interference, RFI. The amplifier's internal circuitry should be designed to minimize the generation of EMI and RFI. This helps prevent interference with other electronic devices in the home. The amplifier should be designed to dissipate heat effectively to prevent overheating. This might involve using heat sinks or other thermal management techniques. Include clear labeling on the amplifier indicating the input and output voltage, current, and power ratings. This helps prevent users from overloading the amplifier or using the wrong power supply. The design should consider the potential for electrostatic discharge (ESD) to damage sensitive electronic components. ESD protection measures should be implemented to prevent damage from ESD events. The design should consider the long-term reliability of the amplifier. Components should be selected for their durability and expected lifespan. The design should be easy to install and maintain. The product documentation should include clear instructions on how to install and use the amplifier safely. The design should comply with all applicable environmental regulations, such as RoHS restriction of hazardous substances and REACH registration, evaluation, authorization, and restriction of chemicals. The design should consider the potential for theft or vandalism. The amplifier should be designed to be difficult to tamper with or remove. The design should consider the potential for accidental damage, such as from dropping the amplifier. The housing should be designed to protect the internal components from damage. The design should consider the potential for exposure to extreme temperatures. The amplifier should be designed to operate reliably over a wide range of temperatures. The design should consider the potential for exposure to humidity. The amplifier should be designed to resist corrosion and moisture damage. The design should consider the potential for exposure to vibration. The amplifier should be designed to withstand vibration without damage. The design should consider the potential for exposure to shock. The amplifier should be designed to withstand shock without damage. The design should consider the potential for exposure to ultraviolet UV radiation. The housing should be designed to resist UV degradation. The design should consider the potential for exposure to chemicals. The housing should be designed to resist chemical damage. The design should consider the potential for exposure to salt spray. The housing should be designed to resist corrosion from salt spray. The design should consider the potential for exposure to fungus. The housing should be designed to resist fungal growth. The design should consider the potential for exposure to insects. The housing should be designed to prevent insects from entering the amplifier. The design should consider the potential for exposure to rodents. The housing should be designed to prevent rodents from damaging the amplifier. The design should consider the potential for exposure to birds. The housing should be designed to prevent birds from damaging the amplifier. The design should consider the potential for exposure to weather conditions. The amplifier should be designed to withstand various weather conditions. The design should consider the potential for exposure to extreme conditions. The amplifier should be designed to withstand extreme conditions. The design should consider the potential for exposure to harsh environments. The amplifier should be designed to withstand harsh environment. The design should consider the potential for exposure to hazardous materials. The amplifier should be designed to be safe to use in environments where hazardous materials may be present. The design should consider the potential for exposure to explosive atmospheres. The amplifier should be designed to be safe to use in explosive atmospheres. The design should consider the potential for exposure to flammable materials. The amplifier should be designed to be safe to use in environments where flammable materials may be present. The design should consider the potential for exposure to corrosive materials. The amplifier should be designed to resist corrosion from corrosive materials. The design should consider the potential for exposure to abrasive materials. The amplifier should be designed to resist abrasion from abrasive materials. The design should consider the potential for exposure to high-pressure water. The amplifier should be designed to withstand high-pressure water. The design should consider the potential for exposure to high-pressure steam. The amplifier should be designed to withstand high-pressure steam. The design should consider the potential for exposure to high-temperature steam. The amplifier should be designed to withstand high-temperature steam. The design should consider the potential for exposure to cryogenic temperatures. The amplifier should be designed to operate reliably at cryogenic temperatures. The design should consider the potential for exposure to radiation. The amplifier should be designed to withstand radiation without damage. The design should consider the potential for exposure to electromagnetic fields. The amplifier should be designed to operate reliably in electromagnetic fields. The design should consider the potential for exposure to magnetic fields. The amplifier should be designed to operate reliably in magnetic fields. The design should consider the potential for exposure to electric fields. The amplifier should be designed to operate reliably in electric fields. The design should consider the potential for exposure to gravitational fields. The amplifier should be designed to operate reliably in gravitational fields. The design should consider the potential for exposure to acceleration. The amplifier should be designed to withstand acceleration without damage. The design should consider the potential for exposure to vibration. The amplifier should be designed to withstand vibration without damage. The design should consider the potential for exposure to shock. The amplifier should be designed to withstand shock without damage. The design should consider the potential for exposure to impact. The amplifier should be designed to withstand impact without damage. The design should consider the potential for exposure to compression. The amplifier should be designed to withstand compression without damage. The design should consider the potential for exposure to tension. The amplifier should be designed to withstand tension without damage. The design should consider the potential for exposure to shear. The amplifier should be designed to withstand shear without damage.